Okay, let's see if we can work through these problems. We'll start with problem number 2. Okay, so we've got the box. I'm going to switch pins here. This is a little thick. Okay, 1, 3, 5, and 7. 1, 3, 5, 7. Okay, we got 400 draws. Estimate the chance sum of the draws. Okay, so the sum of draws will be more than 1,500. Okay, so the expected number of draws is the average of the box times 400. The average of the box is 1, 3, 5, and 7 is 1 plus 3 plus 5 plus 7 divided by 4. That's equal to 4. So if we draw our curve, the average is 4 and you're taking it 400 times, so you're 1,600 right here. And we come down here to 1,500, and they're asking us what is the probability that the sum of the draws is greater than 1,500. So this area under the curve represents the entire chance, so it represents 100%. They're asking us what is the chance that we're greater than 1,500. 1,500 is here, so the area that's greater than 1,500 is all this area right here. And so what we have to do is standardize 1,500. And when you standardize 1,500, you have your they call this your observed value minus your expected value, and you divide this by your standard error. Well, we could calculate, and we know that the standard error is equal to the square root of the number of draws times the standard deviation. We can calculate the standard deviation, or we can just plug it into the calculator and get it. For the sake of time, I'm going to plug it into the calculator. 1, 3, 5, 7. If you calculate your first levels, we got 2.24. Standard deviation equals 2.24. So your standard error then is equal to the square root of 400 is 20 times 2.24, and 20 times 2.24 is equal to 44.8. So if we take this equation right here and we plug our values into it, your observed value is 1,500 minus 1,600, your expected value, divided by 44.8. All of this is equal to, let's do it here, 1,500 minus 1,600, divide that by 44.8, minus 2.23. Minus 2.23. So we're 2.23 standard deviations away from our mean value. Minus 2.23. And that is our z value. Now, if we look up our z value in a table, the table that he gave you or the table in the back of your book, you'll get the area under the curve. And it just depends on how your table is set up. Most of the time you'll get the area under the curve up to that z value. Okay, well the entire area equals 1. So if in fact you look in your table and you look under minus 2.2, and then to get to the 3 you have to go over to the column that has 0.03, and you'll drop down and you should get a value. Let me just calculate in my calculator. Minus 2.23. You should get a value of 0.01287, something like that. Okay, and that is this part, but we want this other part over here. We need this part. So if you take 1 minus this part right here, which is 0.01287, you should get 0.987, and if you times that by 100, it's like 98.7%. Okay, and that should be the answer to A. Let's just scroll this down. For 2B, we have the same basket, 1357. But for this question, they're asking you estimate the chance there will be fewer than 93s. So the only thing that counts is if you get a 3. So if you get a 1, it doesn't matter. If you get a 3, it counts as 1. If you get a 5 or a 7, it doesn't count as anything. The only thing that counts is if you draw a 3, and that counts as 1. So this is going to be our new basket. If we draw our curve here again, let's change color so we don't go to sleep. Our expected value. Our expected value is going to be 100, because the chances are 1 out of 4 that we're going to draw a 3, and we're going to draw that 400 times. So if you take 400 times 1 out of 4, you get your expected value of 100. And it's asking us to estimate the chance. It's a good color. This is a good color. Estimate the chance that there will be fewer than 90. So if you go down here to 90, and this is 90, we want to estimate the chance that there's going to be 90 or fewer. So the first thing we have to do is standardize this. We take our observed value of 90, subtract our expected value, and divide it by our SE, which is SE again is equal to the square root of 400 times our standard deviation. Okay, now this is interesting. What is our standard deviation? Let me just plug it into the calculator again. 0, 1, 0, 0. Okay, our standard deviation then from the calculator, and we can calculate this if we wanted to, but it's equal to 0.433. So our standard error is equal to the square root of 400, which is 20, times 0.433, and that is equal to 20 times 0.433, 8.66. So this is just too dark of a color. So if we go 90 minus 100 divided by 8.66, this was 8.66, and that's going to be, let's see, 90 minus 100 divided by 8.66, 78.45. That doesn't seem right. 90 minus 100 divided by 8.66. Okay, this is better. Minus 1.15 minus, and what's that saying? This is minus 1.15 standard deviations below the mean right here. So this is your z value. So if you go to your table and you look up the z value, it'll give you the area all the way up to this 1.15 under a normal curve. And my calculator has that same function, so I'll just punch it in. Minus 1.15. Okay, and it's it amounts to 0.125. 0.125. That's equal to 12.5%. Okay, I'm going to go ahead and stop this video, and I'll be right back with the next problem, problem 3.